So what do you see when you look at that? Has anybody seen anything interesting? You see a Z, thank you. I've shown this to a number of people and they don't see it till I point it out. Good point. So what is Z? Z is the mainframe, and I'm going to tell you how we ported Go to the mainframe. Some of the talk's going to be pretty low level, close to the metal, but I'm going to have some motivational slides. I just want to tell you that little UFO up there in the corner stands for Linux 1, and I'm going to explain that a little bit in a minute. So what's a mainframe? So here's a couple of my team members. They're working very hard porting Go to the mainframe. Actually, this is from the 1960s. So this is an IBM 360. And if you had a program that you wrote for that machine back then, there's a pretty darn good chance it would still run on our modern mainframes. Maybe when you think of mainframe, you think of the world of Dr. Strangelove. And here's poor Captain Lionel Mandrake trying to save the world from a nuclear holocaust, okay? And here's a spoiler alert, he was unsuccessful. So this particular mainframe was destroyed in a nuclear war. But actually, this is what they look like now. So these are the two primary boxes that we sell. Now, I want to tell you what they're called. They're called Z13. They're also called Linux 1. So we have two names for the same thing. The larger one obviously has more cores and costs more money. The smaller one is the sort of entry level. Z13 is the architecture. Z is the architecture. Z13 is the model number that is currently being produced. And if you buy a Z13, it can run either Linux or another operating system, which I'll talk about in a sec. The larger box can have up to 141 cores with actually up to 640 coprocessors only doing I/O. So it's an I/O supercomputer. And that's, we've seen in our work with Go, we've seen these I/O processors giving us a lot of performance boost, so they're really important. You get electronic isolation on your LPARs. It's called EAL5 plus rating, which is the highest security rating you can get on a commercial machine, up to 8,000 virtual machines, 99.999% reliability. And what that really means is that some of our customers who have had Z and the predecessor mainframes for decades have never had any downtime. They have never had to reboot their computer, okay? It's always been up. And that's why we call it Z, because Z stands for zero downtime. One box can process up to 2.5 billion transactions per day. What's a transaction? So that's when you make a purchase and you pay with your credit card on your smartphone, you check your bank balance, you move money from one account to another. These are all transactions. And in fact, it's mainly banks and financial industries that particularly like the security and reliability of the Z mainframe. So as I mentioned, Linux 1 is a Z13 that only runs Linux. So they load it up with the Linux microcode on each of the cores, and you can't run the other operating system. The other operating system is called ZOS, and it's the one that started out as OS 360 and then became MBS, and now it's called ZOS. And it's just another operating system. But if you're running ZOS, you're not running on a Linux 1 box, because Linux 1 means you're only running Linux. Whoops. The right thing here? What am I doing? Oh, too many. There, I got one. Okay. Here's one of the unique things about this machine. They test it to make sure that it survives an earthquake. So you can actually go to YouTube and see them shaking it as if it were in a Category 8 earthquake. And it's not got to just survive. It actually has to keep running and processing transactions. 96 of the world's top 100 banks, 23 of the top 25 retailers, 9 out of 10 of the world's largest insurance companies all run their business on Z. So that's a lot of large enterprises, and most, in fact, the vast majority of the transactions in the world that happen, whether it starts in your smartphone or on your laptop or you go to the bank, the vast majority of all transactions are running on mainframes. So we have made Linux available on the mainframe, and I'm in the area called ecosystem, so we're trying to ensure that all of these packages that are Linux-based packages, that they also run on the Z mainframe. So we have 3 primary distros for Linux: Ubuntu, Red Hat, and SUSE. We have a large number of programming languages, and here I've got this laser pointer. Let's see if it works. So languages, and we'll see the Gopher. I'm also going to point out this guy. That's what I was doing last year at this time. So last year at this time, Go was but a twinkle in our program manager's eye. So we were doing OCaml. Anybody ever program in OCaml? Oh, thank you. Please do it on a mainframe. You'll use my compiler. Ubuntu actually is distributed with the 1.6 version of our compiler. On version 16.04, Ubuntu on the Z hardware. Go 1.7 is coming, so when it becomes generally, released and you download it, you can build and run it on a Z mainframe. I did want to talk a little bit about GCC Go because it's the other compiler. So, it works. It's a little inconvenient for multi-platform builds because you don't want to have to do something different for Z than you do with all the other platforms. But from a performance point of view, we weren't satisfied with it either. For our target applications, symbolic largely or system stuff, GCC Go is not a very good performer. I think if you wrote a math library in Go, it would work well with GCC Go. But for the stuff we're interested in, it's really not that good a performer. Also, the build times are a lot longer, about 3 times longer than with, I'll call it native Go. Now, if you want to try this out, go to this website. So it's www.ibm.com/systems/Linux1. And you can sign up for a community cloud Linux based Z mainframe. So you can have your own mainframe. I mean, it's obviously going to be shared. You're not going to get 149 cores. You're going to get maybe 2 cores. But you can certainly begin development there and play around with it. OK, so what's why would we bother putting Go on the mainframe? As I mentioned, we want to have Docker and Kubernetes and Juju and Cloud Foundry and all the things that are written in Go. We want them to work well. But I have to say my main driver over the last few weeks at least has been something called Open Blockchain or Hyperledger. How many have heard of Hyperledger? Not so many. OK. Thank you, Michael. I'm just going to give you a little bit of religion on Hyperledger. Mark Anderson, who is one of the founders of the internet, has said that in 20 years' time, we'll be talking about blockchain the way we talk about the internet today. In other words, it's going to become ubiquitous. And another analyst said that next year alone, financial institutions are expected to spend $1 billion on blockchain technology. Did I mention that 96 of the world's top 100 banks and 23 of the 25 top US retailers and 9 out of 10 of the world's largest insurance companies are already running their businesses on Z? And they're going to be wanting to run blockchain. they're already expressing interest in blockchain, much as a deer expresses interest in the headlights of an on-approaching car. So this is going to be big. This will be a very important application. I'm going to give you one slide on blockchain. I'm going to hurry through it. So blockchain is a shared ledger. So you have a number of parties. Previously, they all had their own ledger, and they had to communicate. There was opportunity for fraud. I could have double books. You've heard of that, of course. When you have one single shared ledger, there's no double books. Everyone has consensus about what's in it. Everyone understands where everything came from, so there's provenance. The blockchain cannot be changed, so it's immutable. And once transactions in the blockchain, it's there forever, so you have finality. And blockchains can be used for money, but also things like property, tangibles. You can have almost anything that you want to exchange with other parties and which has value can go into a blockchain. So I'm going to tell you why, how we did the port. Why should I tell you about the port? Because it might amuse you to see how we stumbled around, clumsily at first. There might actually be something we've done that would apply to improving existing implementations. And I think the world isn't done yet with instruction set architectures. Over the years, I've done PDP-11 myself, BAX, DEC 10, General, Data General Eclipse, Multics, Spark, Symbolics, Lisp Machine, that's the old one, Thinking Machines, Connection Machine, you might want to Google that one. Burroughs B6700, PowerPC, and all of the IBM mainframes back to 360. I've done compilers and system software, and I'm pretty sure there's another one coming. Okay, people aren't done with ISAs yet. And there's even still some embedded processors that aren't ARM that haven't got a Go compiler on them yet. So where do we begin? Every teacher starts, every English teacher in high school says, start with what you know. So what do I know? I know PowerPC. So starting last fall, I thought, how am I going to do a Go port? I know PowerPC. I looked at the Go Power port. I sort of mainly basically understood it. Hey, let's just transliterate all the power instructions to Z instructions, and maybe that would work. Of course, I can't do it by myself, so I gather an amazing team. Everyone on this list except Bill O'Farrell is smarter than Bill O'Farrell, so that's the nightmare I wake up to every day. And then here, I'm just going to read out the points at the back. You maybe can't see them. This could be the whole talk. Start with a Big Endian port of PowerPC. Write instructions, instruction gen for Z. Add relocations, cross-compile. Get hello without the runtime. That was interesting. Get hello world to work. Test programs without any pointer escapes because we have no runtime, so we have no heap. Write portions of the runtime in assembler. Cross-compile with the runtime, but with no optimization. Gradually turn on optimization. Gradually tune it for Z. Create a boostrap compiler and finally start running on Z. And continue to write important parts of the runtime in assembler and add specific optimizations. So, in fact, Michael's going to tell you a little bit about that. Remove all the traces of power and then benchmark important applications. So we've been through all of that, and it's an ongoing process. And I'm going to break out a couple of them. So when we started with the power instruction set, we thought we were just overwhelmed with the number of instructions. Now it seems tiny. It's like, oh, there were only about 300. And now we've got over 600 in our port. But back then, it just seemed overwhelming. So what I did was I compiled the Go runtime with -S and generated the assembly for the entire runtime in Power. And I took a big file, I mean, it's gigabytes, sorted it, and found out all of the power instructions required to build the runtime. And I said, let's start with those. And I told my eager beaver developers, I slapped them on the wrist if they tried to do an instruction that wasn't in that list, because we're never going to get through them all, I thought, if we don't pare it down. So those are the instructions that we started with. Those are power instructions. And then we had to decide, okay, Z's been around since the 1960s, and every generation they add new instructions and new addressing forms. And at some point, and the Z13 has some new ones, so we have to decide sort of what generation or cohort to emit. And it just so happened that about 6 years ago, the Z196 came out that has some wonderful instructions. It has, most importantly, PC relative addressing. That is so handy when you're writing a compiler. So what that means is previously, you had to, for addressing, you had a 12-bit displacement. It wasn't negative. It was a 12-bit positive displacement. So if you wanted to address something backwards, you're kind of stuck. And 2 index registers, which means you have double the number of registers than maybe you really need. And this led to a need for putting what are called literal pools in your code. So every 4K or so, you have a chunk of data that if you get there, you have to jump over it. And that's got pointers and things that you can load up for those, for example, backward references. We thought that would be inconvenient. But with this relative addressing, 32 bits of PC relative addressing. So I can go, and by the way, it's half word, so I can go backwards 4 gigabytes or forwards 4 gigabytes. I figured that would be enough, and I think it is, actually. We haven't ever run out of either text or data space with that addressing. If we ever do, then we'll have to revisit that. But so far, it's worked well. So that's our relocation, R390 PC double. So the Linux process layout, where you have text and data, where the data is always a fixed offset from the text. And that's true for shared objects or any executable on Linux. That helped us a lot because I can pre-calculate, even for data, I can pre-calculate the PC relative address of anything. So that worked well in terms of Linux. Byte addressing was an issue because we didn't realize that with half-word addressing, you couldn't address bytes. We had this really weird bug where a byte would be aliased with its next-door neighbor and would manifest in strange ways. So we just made everything half-word aligned. So we did some very simple instruction generation. Often in compilers, when you generate instructions, you have to do a fixed point over the generation step. But we simplified that by using always these full 32-bit addresses, offsets. We turned off all optimization. We tried to figure things out. For a long time, I didn't know why there was sometimes call R12 and then an address. What's the R12? I mean, I didn't actually know what that meant. That is the register associated with closures. And that call instruction is when you're calling a closure and you're telling the peephole optimization not to optimize away R12 because it's really important. So that's the kind of thing of fumbling around trying to figure these things out. Couldn't build the runtime. How do you test a program with no heap? Turned off the function prologue. We used the system stack. We didn't use heap stacks. And we still managed to get Hello World working. Through the magic of the SVC call, or the syscall, on Linux, I didn't know this, but you can print from the operating system directly print onto the screen. So we got Hello World. I'm just flipping through this. This is a print hex program. It's very conventional. It just says I want to print a number in hexadecimal. It's just that every character we use print string, which requires no funct, no runtime, nothing. And you can get Hello World working. This is an example of what the code looked like. Initially, the parts in red are interesting. The first part is the function prologue. I wasn't very happy with the function prologue because the main path involves a jump. You have to check whether the stack needs to grow or not, and then jump to the start of the program, assuming everything's okay. On Z, that's slow. What you want to do is have the fall through go to the start of the program. So we adjusted that later. And I'm just showing you a lot of redundant moves. Move R1 to R2, and then do add R2, R3 to R1, and move R1 to R3. I mean, these can be simplified greatly. I made a database. So we just examined code, reams and reams of code, looking for bad code sequences. And I made a database, and I'm showing you the Wordle. I couldn't show you the whole database, so this is a fanciful way of saying, and a lot of entries. Here's an example. So this is not Go assembly, by the way. This is actual real Z assembly. Here's a whole bunch of redundant moves from one register to another that really does nothing except clear a register. I don't know where this came from, but I made note of it, and by fixing it, we got 3.7% improvement overall. Here's another one. This one is, oh yeah, this is an interesting one. I wondered why we were redundantly loading R1 before a function call, given that R1 was going to be killed, because all registers are killed across function calls. And Michael found out it's a bug, and when he fixed the bug, all of the code shrank by 8%, this one fell swoop, and it was amazing. So we improved about 23% in 5 weeks' time or so. We began to remove the power isms. We turned on some of the x86 style instructions because they were appropriate for Z. Rotates, move immediates, memory to memory operations like MVC, XC. Got rid of the duff operations. Have you ever looked at that in the Go code? Duff 0 and duff move. It's a classic old computer sciencey thing. When you don't have good instructions, you can use the duff style. But we have good instructions, so we got rid of it. We got a better prologue. I wrote big math in assembly. You heard Rob Pike say that this morning. That's one of the main things you got to do is write big math in assembly. Well, I did that. And we began to use the SIMD on the Z13 for certain things. Like CRC32, we got a 55x improvement, 55 times faster with assembly than without it. And we used PEEP to introduce K instructions, which are the 3 operand instructions on Z. So now the code looks a little better. In orange there is the new prologue. It's a 2-instruction prologue, and it has an epilogue associated with it, but that's okay. We never really, very rarely actually get to the epilogue. Okay, I wanted to talk a little bit about basic blocks. In Go, you have to put in a lot of write barrier instructions because of the garbage collection. If you are mutating during garbage collection, you have to do special things, and that's handled with write barriers. I was a little concerned that with all the write barriers, we wouldn't have enough space left in our basic blocks, as it were, to do any interesting scheduling. So I actually did an analysis of competing compilers. So the first one in blue is us, if you can see that. I'll use this. That's us. This funny looking guy, that's GCC. He's got a little bump there as 6 instructions. That's the prologue. Their prologue is 6 instructions long, so that's why that stands out. And these other things are just other compilers, and I'm tracking the number of basic blocks of certain sizes, and it turns out, we're okay, actually bigger than most of them. Maybe that's because we haven't optimized our code enough. But nonetheless, it means that we have opportunities to do some scheduling there. And now we're getting into SSA. So I won't go over this other than to say this piece of code was compiled with an SSA version of our compiler, and is significantly shorter than the other versions I showed you. So we're making some progress there. It's still not ready for prime time, but hopefully we'll get there. Now, I did want to talk about things that are important to us in the Z port. So, as I mentioned, Hyperledger is really important right now, and we've studied it a lot. One of the things that Hyperledger uses a lot of is Go routines. And so, when you have a blockchain, every blockchain has a number of peers that communicate, and the number may vary from 2 to potentially hundreds. So I just plotted up to 24, and the number of Go routines in each peer that they have in order to handle all the concurrent communication that's happening. And it turns out that by the time you get to 24 peers, you have about 350 Go routines. So that's concurrency, not parallelism. But it does mean that scheduling those Go routines is an important consideration for performance. We also found that reflection is really expensive. I guess that makes sense. So reflection is when you call a function by name. Somebody says, please call the function called Mike on that guy over there, and you pass a string over, and then you look up the function by its string name, and then here are the parameters. You have to copy the parameters onto the stack, and then you call the function. It's a simple enough operation. It's just really expensive and actually consumes a lot of the cycles for the blockchain program. So we're trying to look for ways to make that faster. And then the most important thing for blockchain is crypto. Okay? So we had a wonderful talk on crypto yesterday. And so I hope you memorized that. I hope you came and memorized that. Because Michael is going to assume you all know that. About P256 and SHA-2 and AES and CBC and GCM. So all of those, you know all of that stuff. So he's going to tell you what we did for crypto acceleration in our Z port of Go. Take it, Michael.
Hi, so thank you, Bill. Hopefully you know a bit more about the porting process that we did. So as Bill said, one of the things we wanted to do for Z was optimize crypto. So in this talk, I'm going to specifically focus on AES. So AES is part of the crypto AES package, fairly obviously, hopefully. And it's a block cipher. So what is a block cipher? So it's an algorithm that encrypts and decrypts data using a key. It's fixed length, in this case 16 bytes, and it's symmetric. So as opposed to using public key cryptography, we actually use the same key for both encryption and decryption. And the implementation in Go implements the Cipher.block interface. So the block cipher implements the Cipher.block interface. So how do we actually use AES? Well, one option is we just run it in a loop over our data. So it's pretty simple to do in code, in Go, sorry, and this is called electronic codebook mode. So let's run this code on our Gopher. So we want to send it to our friend, make sure no one else can see it, and we get this, which isn't really very well encrypted. So it is encrypted, but because some of the blocks are the same in the input, they're also the same in the output. So we've leaked a bunch of data, a bunch of information about our data. So how do we solve this problem? Well, we use modes of operation. So ECB is one mode of operation, but there are also a bunch of others. So I'm going to focus in this talk on CBC, which is chain mode. I'll talk about that in a bit more detail in a second. Another option, which is very popular, is counter mode. So this is where rather than encrypting the plaintext directly, you actually encrypt counter values with the AES block cipher, and then output, and then XOR your plaintext with those encrypted values in order to encrypt your actual data. And there's also cipher feedback and output feedback modes, which are again slightly different, related to chain modes, but with some slightly different properties. And these all live in the crypto cipher package. So this is what our Gopher looks like when it's encrypted using CBC. So as you can see, just looks like noise. So that's what we want. Lots of data, we need to run it through one of these modes of operation in order to encrypt it properly. Okay, so let's have a look at what Cipher Block Chaining actually does in a little bit more detail. So what we do is we call an initialization vector. We also call it a nonce, a number used once. And essentially we feed that and XOR it with our plaintext, run it through our AES block cipher, and output some ciphertext. But then for the next block, we actually plumb that ciphertext back through and use it instead of the initialization vector. Again, run the block cipher and get some ciphertext out, and so on until we've encrypted the whole thing. And in Go, we do this with two parts. So we create a new AES cipher with a key, and then we create our CBC encryptor using our initialization vector, call crypt blocks, encrypts a whole number of blocks, and so we've encrypted our data. Now, obviously, we were using CBC encryptor before. Now we have decryption. It's slightly different. As you can see, the XORs are after the AES blocks, and we have a slightly different, we have a different name for our CBC decryptor, obviously, but implements the same interface. So they're both implementing the Cipher.block mode interface. So how does this all fit with Z, or Z, depending on how you want to pronounce it? Well, so we have a bunch of instructions on Z which are specifically target cryptography, and these exist in the Message Security Assist group. And you could also see it referred to as the CP Assist for cryptographic function, which is a bit more of a mouthful, or CPAC-F. And each core has one of these coprocessor type things, which will handle a bunch of cryptographic operations. So we've got block ciphers, so DARES, triple DARES, don't use those. AES. We also have modes of operation we just talked about. Hashes, SHA-1 and SHA-2, as Bill said, those are actually in Go now. We also have ghash, which is important for Galois counter mode, which I really went to George's talk yesterday. You'll have heard a bit about. We also have pseudo-random number generation and message authentication codes, and some other features as well, which I won't go into now. Okay, so where do we start? Well, we want to create something simple to start off with. So there's already an implementation of AES accelerated for AMD64, and they work on a block-by-block basis. So you encrypt a single block at a time, and it implements the Cipher.block interface. So let's start there. So we have an ECB mode instruction, which we wrap with some assembly. So just setting up parameters. The only real complexity here is that it can be interrupted, so we actually put it in a loop to make sure that we get through all our data. And then we wrap that in some Go code, which implements the Cipher.block interface. So now we have a block cipher we can use. As you can see, you've got some function codes that we have to pass into our instruction, tell it which block cipher to actually use. And then, the final piece of the puzzle, we need to have a way of returning this optimized implementation when we are able to, so when the system supports the relevant functions. So that's fairly straightforward. So great, so now we have an optimized implementation of AES, right? So, okay, so let's have a look at some of the performance numbers for the instructions that we're using. So as you can see, for very small messages, such as a single block, we're actually getting quite low performance. So we're looking at like low hundreds of megabytes per second. Whereas if we actually use the chain block mode instruction directly, we could get all the way up to sort of around 3 gigabytes per second. So let's look at the assembly for this. So it's a bit more complicated. So Z is very much a CISC architecture. In the instructions can actually take parameters on the stack. Pointers to parameters that then read in and interpret. So in this case, as we mentioned before, we need initialization vector because we're in chain block mode. We need a key, obviously, for our AES block cipher. And again, we've got this loop just in case the instruction is interrupted. So that's good and everything, but how do we call it? Well, so we need to write some Go code. So there already existed an implementation optimized an optimized implementation of Galois counter mode, GCM, for AMD64. And what they were doing was using promotion. They were promoting the AES object to an object capable of doing Galois counter mode. So we'll do the same thing. So we create this new CBC encryptor method on our original optimized implementation that creates a CBC implementation that gives us the initialization vector and the other things that we need in order to do Cipher Block Chaining. And then in the crypt blocks function, rather than, so in the crypt blocks function, we may call our assembly implementation. So that's nice. We have a way of creating our implementation sorry. But now we need a way of actually calling it. Now the problem here is that this is all in the AES package at the moment. We actually created, as we saw before, we created our CBC Cipher mode in the Cipher package. So what do? So we add some code to our Cipher package. So in this case, we add a private interface and just modify new CBC encryptor a little bit to do a type assertion, see if our block cipher actually implements CBC. So great, now we can call it CBC and create an optimized block cipher. So then I submitted this upstream. During the code review, Brad pointed out that we were implementing a private package in the crypto Cipher package, but we don't actually know we don't have any way of telling whether we're actually implementing that interface or not. So the solution we kind of came up with was we define a duplicate private interface in the AES package, and then we assert that the optimized implementation fulfills that interface. So this is a kind of interesting technique that I didn't actually know about before this, where you assert a type, and at compile time it checks that your struct actually implements the interface you're interested in. Okay, and so then we just mock everything up. So we create a mock block cipher, pass it into the CBC encryptor function, and we get back our promoted, hopefully, mock implementation. And so hopefully, no one will be able to break this without realizing. So we've done all this work. What sort of performance boost do we get? Well, we can see from the first step we took, implementing one block at a time, got a reasonable performance boost, maybe 3x. But then if we take that and give a big payload to the hardware, we can actually increase that a lot. So we're talking, well, maybe 15x faster than calling single block mode on it in a loop. Yeah. Yeah, worth doing, I think. So what sort of future work are we looking at? So those of you who went to George's talk yesterday will have heard him recommend P256, which is for signatures. And this is in the elliptic package. So currently this isn't optimized on Z, but so my colleagues, Vlad and Jonathan, have been working on optimizing it for Z, and hopefully this will go into 1.8. So there's some code available already. It's not quite finished, but it's there. And the other thing that's kind of missing from our optimizations at the moment is Galois counter mode, which, again, you will have heard in George's talk. So there's no timetable for that as yet. We have some instructions that we can use to do it. We have some ideas, but we haven't actually started working on it yet, and I'm not sure if it'll make it into 1.8. So I think that is our talk. Thank you very much for listening, and also I wanted to thank the Go team and the Go community in general for being so helpful and helping us particularly with code reviews, things like that, and questions. Thank you very much.